Hello, welcome to the session. My name is Jags Pusapadi and I am a solutions architect at AWS. Today I want to share with you a few things that you should know about our efforts on quantum computing at Amazon. So, what is quantum computing? In essence, quantum computing is a whole new way of processing information. It has the potential to solve computational problems that are beyond the reach of classical computers by using the laws of quantum mechanics. In classical computers, we use a collection of bits to represent their state. Each bit is definitively 0 or 1. In quantum computers, we use more sophisticated data representation known as a qubit or a quantum bit. Each qubit can exist in a state of 1 or 0, but also in a superposition of 1 and 0, meaning that the qubit is simultaneously occupying both states. Although a single qubit could be in a superposition of the two states, when a measurement is made, it collapses and your measurement result is either 0 or 1. Things get a bit weirder when two qubits have a chance to interact with each other. With some interactions, the qubits can become intertwined. In this case, knowing measurement of one qubit could tell something about what will happen when you measure the other qubit. This kind of correlation between measurement outcomes is quantum entanglement. These superposition and entanglement phenomena can be used to perform certain calculations much faster than conventional computers. As we process the information in a completely different way from anything we have done in the past, the way these problems are solved is also new and different. And not only that, this is leading us to the capability of solving new classes of problems. There are particular problems that can be solved much more efficiently using a quantum computer. We need to build extremely sensitive devices, and this turns out to be a really difficult scientific and engineering challenge. This is mainly because we want these qubits to interact strongly with one another, but avoid interacting with the external environment. Both scientific community and the industry are developing on their efforts to close this gap, and new discoveries are being published at a very high pace. So this is an interesting time to be in this field. Quantum computing speed up doesn't mean a quantum computer is more powerful than a classical one. Instead, it has a different model of computation. In this model, relatively new algorithms are designed to solve difficult computational problems that tend to grow exponentially as the problem size grows. Since quantum computing has a really long-term transformative potential, many people are paying attention to it. However, it is difficult to predict which use case in which verticals or industries are going to be most transformed by this technology. And so by starting now, customers have the ability to understand the potential of this new technology and get a head start. Some areas we see quantum computing applications are computational chemistry, quantum machine learning, and optimization in several fields like logistics, finance, and engineering. At AWS, we are humble about the technological challenges, but also excited about their potential. It may take years before we see first commercial applications of quantum computing, but now is the right time for customers to start with quantum computing to research and build expertise. So what we are offering to customers is to start experimenting with quantum computers, cut through the hype, compare different technologies, and explore if and when quantum computing will matter for their business. Amazon Bracket is a fully managed service that allows scientists, researchers, and developers to begin experimenting with computers from multiple quantum hardware providers from a single place. We aim to democratize the access to quantum computing, running state-of-the-art devices in the cloud so everyone can access them. Quantum Solutions Lab is a program that allows customers to work with leading experts in quantum computing, machine learning, and high-performance computing. This program is meant to identify the most promising applications of quantum computing for customers' business and get them quantum ready. AWS Center for Quantum Computing is a research center close to Caltech that is bringing together world's leading quantum computing researchers, scientists, and engineers. The mission is to accelerate development of quantum computing hardware and software. Businesses and scientists today face a number of challenges when they want to work on quantum computing research projects. Amazon Bracket provides a fully managed cloud service that enables researchers to design quantum computing algorithms in a technology-agnostic programming environment. So it is possible to run algorithms on an actual computer from multiple hardware providers built with different technologies. It also allows to easily debug and test on high-performance simulators that use the same programming framework as used with quantum devices themselves. You can also combine and build and test hybrid algorithms that combine quantum computers with classical computing resources of AWS Cloud. It's really easy to get started quickly using pre-built example tutorials and tools such as fully managed Jupyter notebooks as part of the Bracket service. You can also install the Bracket SDK locally on your IDE and get going. From the console, you can control the tasks and also check the hardware QPU devices availabilities. You can also use managed simulators. We currently offer 2 of them besides the local simulator. This allows you to debug and test your code before running it on the real thing. Finally, this feels just like any other AWS service. So Bracket comes fully integrated with monitoring, storage, and security tools. You can monitor the state of your tasks and use EventBridge to send notifications. You can collect and test results in JSON format from S3, and it's integrated with IAM for tighter permission controls. Amazon Bracket provides access to both annealing and gate-based quantum computers. You can solve quantum annealing problems using the latest QPUs from D-Wave. For gate-based quantum computing, you can access trapped ion technology from IonQ and superconducting quantum processors from Rigetti. Changing between one or another just takes to modify the ARN using a single line of code. This helps you test different technologies and compare the computing performance of different machines for the problems that you're trying to solve, and choose the hardware system that is best suited for your application. In the fullness of time, Amazon Bracket will continue adding more hardware designs for customers to use. You have alternatives to actual QPUs if you want to test your circuits first, or prefer to access a noise-free environment before trying the actual quantum devices. With Amazon Bracket, the simulators come in 3 flavors. Local simulator, this is part of the SDK, and the tasks run directly in your the local machine, and this is very useful for rapid prototyping and testing. The results are computed directly in the machine, so it could be where your Jupyter notebook is running. So it could be the managed notebook or your local machine where if you install it locally. The first of the managed simulator is called a state vector simulator, SV1 for short. It stores the full wave function state and sequentially applies gate operations. It stores all possibilities. The runtime for a task increases linearly with the number of gates. The next simulator is called a tensor network simulator, TN1. This encodes quantum circuits into a structured graph. The nodes consist of qubits and gates. The edges represent connections between the gates and or qubits. Hybrid quantum classical architectures are starting to be so important nowadays. This is because even though quantum algorithms can achieve exponential speedup for some problems, the current quantum hardware adds a lot of noise to the calculations. Hybrid algorithms use an iterative approach, with quantum computers acting as co-processors to classical computing resources. This helps to mitigate the effects of quantum errors. The model is similar to the way GPU complements a CPU in a ML pipeline to minimize an objective function. We let some parts of the algorithm run on a QPU to solve some specific problem, and then rest run on the CPU. This is a very powerful idea. We actually don't program the circuit directly. Instead, we prescribe the circuit architecture and let the classical algorithm iteratively find the best circuit within those bounds. The benefits of hybridization are double. We are not only reducing the resources, but also outsourcing calculations to error-free classical computers that use well-known optimization algorithms. To help you get started with hybrid algorithms, AWS Bracket supports Penelate, an open source software framework built around the concept of quantum differentiable programming. This concept allows you to train quantum circuits in the same way that you would train a neural network to find solutions to computational problems in quantum chemistry, quantum machine learning, and optimization. Penelate is performance optimized for AWS Bracket and provides interfaces to familiar machine learning tools, including PyTorch and TensorFlow. Anyone can get started with the service easily. There's a constantly growing library of notebooks that users can choose to get started, from the basic Hello World to more advanced hybrid and optimization problems. With that, let's get into the demo. I'm logged into the AWS Management Console. Let's look for Bracket and go into the Bracket. Search for Bracket and get to the Bracket service screen. So Bracket is available in 3 different regions: US East 1, US West 1, and US West 2. So when you get into the service page, you see multiple options: devices, notebooks, and tasks. Let's look at devices page first. So here the QPUs and the simulators are listed. You can click into each of them to find out more details about them. For example, D-Wave, it talks about the ARN, which we'll be using in the notebooks, and also availability and the pricing information and which region this is accessed from. Let's all look into one of the gate-based QPUs. So IonQ is based out of US East 1 region, and the ARN is available. In addition, we also see the topology of the qubits and some additional calibration information. Let's get started with some notebooks. Creating a notebook is fairly straightforward. You give it a name, select the instance type. I'm leaving it at default for now. And you can either choose an existing role or choose to create a new role and then create notebook instance. That's it. It takes about 4 or 5 minutes to create one. So instead of waiting, let's go to an existing notebook. Then Manage Notebook comes pre-installed with Bracket examples. Let's begin with Getting Started folder. Here you will find some Hello World examples, how you can run different circuits on simulators, on QPU devices, and also a deep dive into anatomy of the quantum circuits and how to use the SDK and different features. There's also an example of a superdense coding algorithm here. Now let's move on to advanced circuits. So here we have examples covering Grover's search algorithm, quantum Fourier transformation, and quantum phase estimation. There are other examples on hybrid quantum algorithms, QAOA, VQE examples as well. And there are some examples from Penelate. Let's build a simple circuit in a brand new notebook. So let's open a new notebook. We'll start with some imports. We'll next define a device where we'll be running our circuits. Let's go ahead and create our first circuit. So here we'll create a circuit with a NOT gate. In bracket, all circuits start the qubits from state 0. What we will do here is apply an X gate to qubit 0. So you have defined the circuit, and you can see what it is doing by printing the circuit. So what's showing is it's qubit 0 and it's got an X gate. Now to run the circuit, we will define a task and say device dot run, the circuit name and number of shots. So how many times should we run this circuit? So I'm going to run for 100 times and let's run it. So it has run. So we'll get the results from the task. Now let's print the results. As you can see, we have run 100 times and all 100 times, because we have got an X gate, the 0 beginning state has converted into 1. So NOT gate changes a state of 0 to 1 and 1 to 0. Next, there is something called a Hadamard gate, which puts the qubit into an equal superposition of 0 and 1. So let's use that. So now we'll define a new circuit, but instead of X gate, we'll apply a Hadamard gate and follow through with the same steps as before and run it all in one go. So here you can see we have run 100 shots and the Hadamard gates puts the qubit in an equal superposition, and when you measure it, it has got 50% chance of getting to 0 and 50% chance of getting to 1. And as you can see from the results, roughly 50-50, 50 times the measurement was 0 and 50 times the measurement was 1. So here we have seen the effect of superposition. And let's look through some of the examples of existing example notebooks. Let's get started with an hello world example of quantum computing. So here we're going to prepare a maximally entangled build state. So we'll start with imports. And then we'll prepare the circuit with a Hadamard gate as we saw earlier. This puts the qubit 0 in superposition. Then we apply something called a CNOT gate, which is a two qubit gate. So this does a NOT operation on the target qubit if and only if the control qubit is set to 1. So here the control qubit will be 0 and the target will be qubit 1. So let's create the circuit and let's also print the circuit to show. So here you can see a qubit 0 has got a Hadamard gate and it's a control NOT operation. Now let's set up the device as a local simulator and run and see the results. So here you can see you'll never find the two qubits in different states. So you can see half the time both the qubits are in 0 or both the qubits are in one state. So this is to visualize the results. Now we have seen both superposition and entanglement in action. Now let's do a quick view of non-gate based quantum computing called quantum annealing. So here this operates in different ways. There are no gates. Let's use D-Wave for solving a graph partitioning problem using quantum annealing. In quantum annealing, the problems are encoded in QUBO format. QUBO stands for quadratic unconstrained binary optimization. Let's get started. So we'll run with some imports. So here Bracket uses Ocean plugin, which has integrated D-Wave samplers with Bracket. We'll set up some more libraries for graph related tools. One thing that's needed when you start using either managed simulators or QPUs is setting up a bucket. When you sign up for the service, there's an option to set up a bucket and you can define a bucket name. So I already have one. I have given the bucket name here and a prefix for my results to be stored. We'll set that up as well. And then here we are using the device ARN for D-Wave. So this particular problem, there are some helper functions to get the graph and also coloring the graphs. So let's set up the problem. So here we are creating a graph with 20 vertices. And we are generating a random graph. And let's see what we get. Right, so we have a 20 node graph created. The aim is to split this graph into two groups, blue and red. And the aim is to create two such sets with minimal number of connections between the sets. So this problem is embedded into a D-Wave QUBO format using Ocean plugin's sampler functions. And it's now actually running on D-Wave QPU. It has finished. It took 9 seconds to actually run. Let's print the samples. This is the results. So here we have seen the results. You can verify with multiple runs to make sure you get the optimal results. So here we have seen a real quantum computer in action, which has solved a graph partitioning problem. That's all we have time for, but there are many more examples for you to explore using Penelate and more advanced circuits as well. With Amazon Bracket, you have access to quantum computing resources on demand without upfront commitment. You only pay for what you use. There are two concepts you need to know when considering pricing: a quantum task and a shot. A quantum task is the atomic request to a device. So for gate-based quantum computing devices, this includes the quantum circuit, the measurement instructions, and the number of shots. For annealing devices, it includes the problem definition, the number of shots, and other optional parameters. A single circuit execution and measurement is called a shot. So the number of shots or repeated executions for a circuit is chosen based on the desired accuracy of the results. So we've got an example of a calculation to give an indication of how much it would cost. In summary, customers are looking to learn by doing. From a small POC to specific use cases, they can get started building quantum-inspired solutions that could be directly applied to big-scale problems once the quantum hardware allows, and building intellectual property along the way. Amazon Quantum Solutions Lab have partnered with companies with different specializations, including computational chemistry, machine learning, and optimization. In addition to quantum computing, these partners have expertise in quantum classical systems, quantum-inspired classical approaches, and also high-performance computing to help customers develop a plan for their organization. The Amazon Quantum Solutions Lab will help identify and collaborate with the right partners for each business. I hope this has been useful and interesting. Thank you very much for your time and enjoy the rest of the summit.